So we're really happy to have Luca Delacretaz visiting us from Stanford on an overnight flight, here to tell us about the hydrodynamics of condensed matter systems.
Thanks for the introduction and thanks for the invitation to speak here. Had some trouble to get here, but at least I made it on time for my seminar. So I'll try to give a rather general introduction, since I realize that not a lot of people here might be familiar with the subject. So I'll talk about how hydrodynamic techniques have been used recently to address challenges in condensed matter. So it's the same techniques and ideology that we've used in hydrogen physics, for example, to understand quark-gluon plasmas or other strongly coupled systems, but that are now studied in very different systems. And I think why hydrogen physicists should be excited about this is that we're getting more and more examples of condensed matter systems that have strong interactions and that we can actually do experimentations on. So it's a great playground to test non-perturbative ideas on field theory and hydrodynamics in particular. So I'll start with a rather general introduction, and then I'll give a few examples of applications based on some of my research with some various subsets of these collaborators. So Sean Hartnell is my advisor in Stanford. Anna is a postdoc there. Andre works at University of Chicago. Les is in Sweden, and Richard. So condensed matter physics is often defined as the study of phases of matter and transitions between them. What this means in practice is that you're going to have to study systems with interactions, and even typically strong interactions, because you need things to drive transitions, these transitions. And one is typically interested in adding disorder or background fields, like a magnetic field, to these systems. And these seemingly simple ingredients lead to some of the most challenging problems in physics, or at least in condensed matter physics, such as high temperature superconductors or transitions between fractional quantum Hall plateaus. And so the traditional approach to these problems is what we would call a top-down approach in energy physics, which is to stipulate a microscopic model, so guess the degrees of freedom. Here I wrote some version of the Hubbard Model, which is pretty popular in high temperature superconductors. So there's a boson with some self-interactions. And then, what can one do with such a model? Well, you can do perturbation theory in the interaction. Sometimes there's a large N expansion that can help. So you just, if I have several copies of this boson, some diagrams might factorize. Finally, more recently, there's been dualities in 3 dimensions that can be helpful to study strongly coupled systems. And if none of this works, we can always use numerics like Monte Carlo simulations. So to this list, in the past decade, there's a new item has been added, which is the field of AES-CFT. And I think one way to view it now is as a way to generate microscopic models. Okay, you don't necessarily know what the connection between these models and the actual systems you want to describe is, but it's a way to make a guess for microscopic models where you can actually compute things like correlators or connectivities. But I'm going to focus more on bottom-up approaches, where the degrees of freedom are imposed on us by symmetries, for example, by spontaneous symmetry breaking. So hydrodynamics is an example. Another example of these ideas that's been developed a lot in the past decade is effective field theories for quantum critical points, where you basically want to describe a transition between 2 phases. You know well degrees of freedom in the phase, and then you just add some simple degrees of freedom that become strongly interacting to try to capture the physics of the transition. So I should emphasize that these last 3 bullet points don't rely on the existence of quasi-particles. And what I mean by quasi-particles here is quanta of some weakly interacting field that I have in my Lagrangian. And I think it's important that we have such descriptions that don't rely on quasi-particles. And one reason to see this is because of critical points. So critical points are typically described by interacting conformal field theories. The canonical example in 3 dimensions is the Wilson-Fischer transition. So it can be described with this 5-4 type action. So you can imagine that I have just a free scale in the UV with 2 relevant deformations. Those are both relevant in 3 dimensions. And I just imagine flowing to the IR. There's an interacting IR fixed point, which is a CFT that can be thought of as describing the infrared of the system at the fixed transition. And what I mean by that is that if I have an actual system that I think is described by, effectively by this action, I can imagine tuning having these two tuning parameters as like experimental knobs of my system. Let's say I fix one of them, I fix lambda to have some value, and if I tune m, I'll go from from this region where in the IR I'm described by the gapless space. So for small f squared, I'll have Goldstone boson. This has well-defined quasi-particle poles in the Green's function. Similarly, this phase is gapped, but also has well-defined quasi-particle poles. But at the phase transition, we know that something different happens, and the Green's function instead has Brownish cut, because the field requires an anomalous dimension. This is an example of a region in parameter space where there's no quasi-particle. There's definitely no quasi-particle description of this point. So you may say that it's a very fine-tuned point, and indeed it is. But the important point here is that as the temperature is increased, the effect of a quantum critical point on the parameter region that's described by this quantum critical theory is enlarged. So let me quickly go through this argument. As we know, at the critical point, there's a correlation length and a correlation time that diverge. So here G measures the distance to the critical point. Let's say I'm tuning n, and this is some critical exponent. So if I'm not quite at the critical point, let's say I'm around here, and I don't, so in the deep IR, I'm going to be described, the system's going to be described by some phase. But if I look at intermediate times, if I only probe times that are, long compared to microscopic timescales, but small compared to this correlation time, then the system will still seem quantum critical. Okay, and the important point is that now if I imagine putting my quantum field theory at final temperature, so imagine putting it on some thermal cycle, the longest timescales you can probe are of order 1 over the temperature. Okay, and so as long as so if I plug this in here, the system will seem quantum critical as long as the distance to the critical point is smaller than the temperature in some units. Okay, so as the temperature increases, there's a larger and larger region that's controlled by the quantum critical theory. This is what's called the quantum critical fan. So here I have some phase diagram. This is G is my coupling. Here I have a quantum phase transition. This is the quantum critical fan that exists. So in the quantum critical fan, typically you can have some poles that reappear in Green's functions. We'll see hydrodynamic poles, for example. But it's definitely not obvious that that you should think of them as quasi-particle poles. That's the approach I'm taking. Okay, so let me talk a bit about hydrodynamics. So I think a very nice way of understanding hydrodynamics is as an effective field theory, or a dissipative effective field theory of Goldstone-like excitations. At least that's how I would kind of present it to high energy physicists when I'm applying it to Einstein. And in fact, in the case without dissipation, it was formulated exactly like that. You can get hydrodynamic equations from an action principle. It was done, for example, by these authors, where the fundamental fields were basically the coordinates of the fluid. But incorporating dissipation is much more complicated because the evolution won't be unitary. So one thing you can do is couple your fluid to a hidden sector and then integrate it out and have some kind of non-unitary evolution with the remaining degrees of freedom. And more recently, there's been a lot of effort by these two groups in formulating hydrodynamics as a quantum field theory as a specific quantum field theory on a Schwinger-Kelvich contour. So they found a lot of rich structure in this formulation, but in terms of pragmatic calculations, in terms of getting conductivities, getting Green's functions, I don't think this is developed enough to be useful at this point, but it is very interesting. These are very interesting developments. So there's a simpler pragmatic way if you're just interested in getting correlators, which is kind of like in hydrogen when you do current algebra instead of working with effective actions. So like we treated pions before having the Carol Lagrangian, for example. And so the idea here is to work directly with operators, with slow operators. I'll be more specific later by which operators I'm keeping in my description. Some operator relations that they satisfy, such as word identities, and then guesses for their expectation values. So instead of, if I write down an EFT, I would use symmetries to constrain the terms I can write down in my EFT. Here instead, I'll use symmetries to constrain what I can write down in expectation values of operators. And this will kind of shortcut the way to the answer, to getting Green's functions. So as an example, let me imagine that I have as a simple example, let's imagine we have a strongly interacting quantum field theory with a single conserved charge, single conserved U1 charge. So since it's strong, and I'm also putting it at finite density and finite temperature. So since it's strongly interacting, I would expect basically all quantities to thermalize extremely fast, except those that are conserved. For example, the total charge of the system cannot thermalize; it's just constant. And for that same reason, if I have a small variation of charge density, it will thermalize slowly because the total charge is conserved. The local changes of charge density diffuse instead of thermalizing exponentially fast. So that's the only operator I'm going to keep in my description, since I'm interested in very long time dynamics. So it satisfies the word dynamics. I know that it's connected to the current. The current, however, can be a fast operator in general. And so instead of putting it in my description, I'll write down an ansatz for its expectation value in terms of my slow hydrodynamic operator. Okay, so I'll just write down the most general thing that's consistent with symmetries. Here I assume is entropy in a gradient expansion. And so I'm doing things in a gradient expansion because I'm interested in the low frequency, long wavelength observables anyways, so it makes sense to write down this expansion. Now if you plug this in the word identity, you'll get a diffusion equation for charge. Okay, so we derive diffusion of charge in this pretty general case. And you can also find that the Green's function, the charge-charge Green's function, will have this diffusive form, so it has a diffusive form. And it's also very easy to compute connectivities in this framework. I'll just write it down. It's good to keep on the board. So connectivities are defined as current Green's functions. As this particular method of current Green's functions. So there are some other definitions, but I'll just use this for now. I can use a word entity again to write this in terms of a charge-charge Green's function. Okay, now if I plug in this diffusive Green's function in here and take the k goes to 0 limits, I'll just be left with basically the diffusion constant and then I, which is a second. So what this is saying is that the connectivity in diffusive systems is just frequency independent. So this is the definition of the connectivity. It's frequency independent, and it's given in terms of the diffusion constant. So this is typical of hydrodynamics, where there's unknown parameters that hydrodynamics won't tell you, won't give you an expression for these, but they will appear in several different observables. So the assumptions can be tested. Okay, so this brings me to the question of observables. So connectivities is basically the favorite observable of experimentalists because it's the easiest thing to measure. Basically just plug in two leads in your system and drive a current, measure the voltage. You can look at the dependence of the connectivity on frequency. You can also look at the temperature dependence on B fields, etc. And even though it's such a simple thing to measure, it gives you very non-trivial information. Right? It tells you, within linear response, it tells you about 2-point functions of a possibly strongly interacting quantum field theory. And for that reason, it's typically very hard to compute in the context of quantum field theory. But that's not the case in hydrodynamics. Hydrodynamics just directly gives you connectivities. And what's great about hydrodynamics is that it directly relates assumptions about symmetries of the system. So fundamental assumptions about which symmetries are there, which ones are spontaneously broken, to observables like connectivities. So to build some intuition of what connectivities look like, let me start with the oldest model we have of conductors, which is due to Drude. So imagine that conductors just work with quasi-particles carrying, so that the current in conductors is carried by quasi-particles, which collide with impurities with a mean free time tau. Okay, and if you, and so this Drude model leads to a frequency-dependent connectivity that has this form. So I'm going to ignore the prefactor. Let's just look at this frequency dependence. So if I take the frequency to 0, this will go like tau, like the mean free time of the quasi-particles. So that if the quasi-particles are completely free, the DC connectivity is infinite because I don't need an electric field to sustain the current. Okay, and more generally, if I have a finite tau, then if I take the real part of this expression, I'll have a sharp peak around zero frequency. And the height of the peak will go like that. Okay. So you might think that these sharply peaked conductivities are an artifact of my assumption that there's quasi-particles. This peak is kind of like, this flow is like a quasi-particle pole. But it turns out that it's not the case. If I consider even a strongly interacting quantum field theory, where I have translational invariance, and if it's at finite density, then because the current generically carries momentum, and momentum is conserved, the current won't be able to decay, and I'll have an infinite DC conductivity. Okay, and if momentum is not quite conserved, if I add a bit of disorder, but it's, let's say translations are weakly broken, so that the operator P dot is a small operator in any expectation value, then I'll still have a very large DC conductivity. Okay, and the reason is that, so P decays very slowly. J is generically can be a very fast operator, so it's going to have some short time transients. But in any expectation value of a state at finite density, the long time behavior is going to be controlled by the slow decay of P. Okay, and you can, this notion of kind of the current carrying momentum of overlap between two operators is summarized in this expression, which one can obtain from hydrodynamics. Here, this is a susceptibility between the current and momentum, which characterizes the overlap between these two operators. It turns out to just be given by the charge density. So whenever I have a background charge density, the current overlaps with momentum. Okay, notice that I have, again, a Drude-like conductivity. It's basically the same expression. I didn't have any fuzzy properties. So this is basically the strategy of hydrodynamics, is to, we don't want to give a complete description of the system, that would be way too hard. So instead we focus on all the slow operators of the theory that can carry current, that can overlap with the current. So I should mention that it doesn't have to be, that slow operator doesn't have to be momentum. For example, in a superconductor, the supercurrent can play that role. So the supercurrent is just the gradient of the Goldstone that you get from spontaneously breaking the U1. If I integrate this over let's say my system, my 2D system, this will be the winding of the phase across the system, which is topologically protected. So it's just conserved in the superconducting state. But what happens in a superconductor, in a 2D superconductor, when I heat it up, there's proliferation of vortices, and these vortices can unwind the superfluid phase. Okay, so deep in the superconductor, this operator is conserved, and I have again an infinite DC conductivity. But when I allow for topological defects to proliferate, it will start to relax, and I'll have, here I call the relaxation rate big omega. And in the limit where this relaxation rate is small, this is what the low frequency conductivity is going to look like. Okay, so generically there can be several operators that overlap with the current, and so they're all going to lead to different hydrodynamic descriptions. Any questions so far? Okay, so that was the introduction. We learned about non-classical techniques and the role of hydrodynamics. So now I'll give two examples of applications of these techniques. One will be to high temperature superconductors, and one will be in fractional quantum Hall states, where we'll talk about the Hall viscosity. So let me start by explaining what a high temperature superconductor is, since it's mostly a high energy audience. So first, some history. So superconductivity was discovered over a century ago, and it took about 50 years to understand theoretically. We now understand it using the Bardeen-Cooper-Schrieffer theory, which basically can be explained as a quantum field theory of fermions, which are the electrons, that are coupled with the Yukawa coupling to phonons. That's the lattice vibrations. And the Yukawa coupling is marginally relevant. So when I flow to low energies, it grows until some critical energy scale, where it becomes very large. And this is what defines TC. So there's a hierarchy. So the same way, it's like in chiral symmetry breaking in QCD. There's a hierarchy between the cutoff, which is the maximum frequency of the phonons, and TC. And so here, lambda is the Yukawa coupling. So typically, this is several orders of magnitude smaller than the cutoff. And because of this hierarchy, the highest critical temperature you can have for a BCS superconductor is of order 30 kelvins. And so about 30 years later, materials with much higher temperature, critical temperature, were discovered. And for that reason, it's thought that they're not described by ECS theory. And so if we extrapolate the dates, it's going to take about till 2030 to explain high TC, so it's not too late to join the race if you're interested. So that, yeah, the question is not just to explain why the critical temperature is so high, but also how in the world can electrons with Coulomb interactions lead to such a rich phase diagram. So there are some regions that we understand, like this region here. So I should say this is temperature axis, and this is doping, which is basically telling you about how many charge carriers you have. So there's a region here we understand as a Fermi liquid, so that's just weakly interacting electrons. This is an antiferromagnet, which is an insulator. The electrons are trapped in their potential. This green thing is the superconducting dome. Notice that TC, the critical temperature, is pretty high in Kelvin. There are regions where other symmetries are spontaneously broken. So charge order and spin order means that the translation symmetry is spontaneously broken, either by a charge profile or a spin profile. And finally, there's the infamous strange metal region, which has a linear in temperature resistivity. This is the DC resistivity versus temperature. And an important feature of this resistivity is that it violates a bound on resistivity due to Montiel and Rego that you can obtain if you assume that the current is carried by quasiparticles.
So how much does ADS-CFT explain high DC superconductors? I know that there are examples of high
Yeah, so
DC superconductors.
there are models that get linear in temperature resistivity, and so they evade this because they don't have quasiparticles. I think there's several things there's no crossover between a Fermi liquid. I don't know models that have a crossover between a Fermi liquid behavior and a strange metal behavior. And I don't know to what extent the model will convince people that that is correct. I think, so I think there definitely are models that have linear in T resistivity, but they also there's a lot of other observables that can be connected. So you can look at thermal conductivities and ratios between these things. There's a lot of data that has to be reproduced, and I don't think there's any that can do all of it.
Not even a D-wave superconductor would help?
So yeah, I might not be aware of one, but there's, maybe we can talk if you have a particular model in mind.
It's not my model, but it's in the literature. I know that there are DS, different types of superconductors.
Yes, definitely you would need D, but I don't know if there's one that's right. Yeah, so the fact that this bound is completely disregarded by the strange metal phase, right? There's no the resistivity doesn't seem to care about this bound. It's very suggestive that you'll need a non-quasiparticle picture. So our goal in applying hydrodynamics to this problem is not to explain the whole phase diagram from a microscopic model, but instead to use the fact that hydrodynamics relates fundamental assumptions about symmetries to observables to figure out which symmetries are relevant where. Where do we have order? A certain type of order. Okay, for example, I talked, the superconducting region has a supercurrent which is conserved, and I mentioned extending this region by allowing for topological defects that relax the supercurrent. This is what's called a fluctuating superconductor. And you could ask which region of the phase diagram is described by this type of theory, where there's an almost conserved supercurrent. But the question I'll address today is to try to figure out what theory of hydrodynamics describes strange metal. So this is, I think, it's almost a question that should come before trying to make a model, whether it's a ADS-CMT model or a microscopic model. It's a question about the symmetries. What symmetries does your model need to have, or what symmetry breaking does your model need to realize? And so one of the starting points is precisely these large resistivities, which are also pretty confusing from the point of view of hydrodynamics. Because recall that if we have a clean system, almost conserved momentum, the DC conductivity goes like 1 over the momentum relaxation rate, which is pretty large. So they should be good conductors. But strange metals are also called bad metals because they're bad conductors, right? The resistivity keeps on going up. So from the hydro perspective, it's pretty confusing, right? Because you would expect these systems that are clean, and there's evidence that these systems are rather clean, to be good conductors. And so our claim that I'll try to explain is that the correct hydrodynamic description is one of fluctuating translational order. So what I mean by this, translational order means that momentum is spontaneously broken, and fluctuating means, like in the superconductor, that I allow for topological defects. So with spontaneous symmetry breaking come compact bosons, and they can have defects. Good, so I'll try to present. Okay, so I should mention, especially if there's condensed matter people in the audience, that hydrodynamics is not really the mainstream thing to do, and for a very good reason. So for hydrodynamics to be valid, you need a separation of length scales and time scales. In particular, you need strong interactions, so that the electron-electron mean free time is very small, and smaller in particular than the momentum breaking mean free time. So I have to imagine that there's many electron collisions in this kind of semi-classical picture before they collide with impurities or the lattice, or lose momentum with club scattering. And so if this hierarchy exists, then hydrodynamics will be a valid description at timescales much longer than the electron-electron free time. So this typically does not happen in most materials. Probably 99% of materials that exist are just too dirty and are very well described by non-hydrodynamic techniques, either by thermoliquid theory or by other theories. But if for some reason either electron interactions are enhanced or the system is incredibly clean, then it can be a correct description. It has described successfully several systems, even recently. And so our kind of standing assumption is that it could be that high temperature superconductors, at least in some parts of the phase diagram, are described by hydrodynamics. At least this assumption gives us a handle on the problem. Okay, so as I mentioned before, in strongly coupled systems, we expect everything to thermalize very fast, except a few slow operators, which are related to conserved charges. So the bullet points of hydrodynamics will be to first list these long-lived operators that depend on the symmetries you're assuming, and write down their continuity equation. Write down constitutive relations for the currents. That's again where the symmetries come in. And finally, find the Josephson Relations, which are hydrodynamic equations and motions for your Wilsons. So I'll go through how this works for the specific example of hydrodynamics with translational order, which is the theory I want to sell to you. Okay. So
this is generally a bad approximation, but what about, aren't you going to apply it to the steering model?
Yeah.
So for those that don't, it is a good approximation?
Well, that's an open question, but we know that quasi-particle, doing perturbation theory with long-lived quasi-particles is probably a bad idea. And so there aren't that many non-quasi-particle techniques out there. So yeah, you could think of an ADS-CMT model, but even an ADS-CMT model will have a hydrodynamic limit. So yeah, it's a reasonable. I mean, if these systems can be made sufficiently clear, there's always going to be a hydrodynamic limit. Even if a quantum field theory is not really strongly interacting, if I wait long enough, it will look hydrodynamic. So this is the only thing that I believe. Yeah, I think for there to be such rich and unusual, physics happening, my guess is that it's valid, but that's it's still debate. Okay, so those are the conservation laws that I'll assume. I'll assume that I have conserved charge density, energy density, and momentum density. I'm writing it in a non-relativistic notation, not because, you can assume Lorentz endurance, but even if you do, we treat charge densities in a special way because they're going to be the slow hydrodynamic operators. And I actually won't assume Lorentz endurance anyways. So those are the slow variables, and in addition, there's the Wilson modes for spontaneously broken symmetries. Okay, so if I break translations, for example, let's say I break translations down to discrete translations, then I'll have a goldstone that lives in the quotient space. Okay, the condensed matter jargon for this symmetry breaking pattern is a charge density equation. And so, as usual, goldstones are always conjugate to the charge densities for the symmetry that they break. So I'll have this commutator between the momentum density and my goldstone. this one. This extra term just comes from the fact that momentum acts like momentum as usual. Yes? This is the energy density. Yeah, I could have written this whole thing as just d mu to mu naught equals this. Depends what audience I'm.
Yeah, J is actually like up to 0.
So if, yeah, so that's one important comment. If I have Lorentz invariance, the energy current is actually the same thing as the momentum density because the stress tensor is symmetric. But in general, it's not the same operator. Okay. So this is charge density, energy density, momentum density, and then these are the associated currents. Okay, so if I break translations in both directions, similarly I'll have two goldstones with these symmetry breaking, with these commutation relations. And so the same, so you can view these goldstones as being basically as the coordinates of my system. And their deformations are their variations are deformations of the system. So the same way that in, for example, in inflation, because time translations are spontaneously broken, you have a preferred clock. Here, I have a preferred grid of my system. And I'll use the scales. Okay, so to summarize, we have our slow operators are charge density. Here I wrote down entropy density. I can trade it, with these things for using thermodynamic identities. Momentum density and gradients of my goldstones. And they also have thermodynamic sources. So this is an equivalent set of variables. They're just related by some matrix with a linear response.
So charge density with the first
Oh,
one?
yeah, so the condensed matter jargon for this is a Wigner crystal. It just means you're spontaneously, electrons are spontaneously breaking translations in two directions. So charge density way and Wigner crystal. Okay, so now that we have these conservation equations, we need to close them to get equations of motion for the charge densities only. And so for this, we'll need considerate relations for the currents. Okay, and how do we do this? Well, without making any additional assumption, we'll just write the most general thing possible. So this is where we'll parameterize all our ignorance. There's going to be a bunch of parameters that the hydrodynamics won't tell you about. If you have a microscopic model, you can give expressions for them. They also, satisfy some inequalities. You can use hydrodynamics to show that these have to be positive, for example, for entropy production to be positive, but otherwise they're not fixed within hydrodynamics. So we'll write down these considered relations for all currents and plug them in here. So notice that here I wrote linearized considered relations. This is because I'm just interested in linear response, so that will be sufficient for my purposes. But you can, of course, do nonlinear hydrodynamics. And then, so here, this is also, in these expressions is where all the symmetries come in. So I can assume, for example, if I assume relativistic invariance, I would write covariant expressions. Galilean endurance is more tricky, so there's a word identity that comes with Galilean boosts, which turns out to impose that the current is just proportional to the velocity.
Can you quickly just run through and say whatever you mean? So you have charge density, velocity, and what?
Yes. So here I'm going to write everything I can in a gradient expansion. My variables are these. I have these, so I have one vector. I have velocity. This is the chemical potential, which sources the charge density. Temperature sources entropy. And this is the goldstones, and this is just the source of the goldstones, which is goldstones. So these are all scalars, so I'll just put gradients of these scalars. Phi is a vector because I'm grading two transitions. And then all these coefficients are unknown. Okay, so we're almost done. The only guy that doesn't have an equation is the goldstone. So hydrodynamic equations for the goldstones are usually called Josephson Relations. Let me just quickly see how it works in superfluids, because that might be a little more familiar. So in the case of a superfluid or a superconductor, phi is conjugate to the charge density, since we're spontaneously breaking V1. And the charge density is sourced by the chemical potential of the Hamiltonian. Right? This is just an A mu J mu term, basically. So that if I compute phi dot using the commutator with the Hamiltonian, I'll find that phi dot is given by mu. So This is true at equilibrium. Out of equilibrium, there'll be higher gradient terms. Okay. So when I break translation symmetry, my phi's are conjugates to momentum density. And this momentum density is sourced by velocity. Okay, that's the thermodynamic source for momentum density. And so phi dot will be given by V plus higher gradient terms. So this is pretty intuitive, right? If I look at my grid, if I have a deformation of the grid that depends on time, the time derivative is just the velocity. And so now we have closed hydrodynamic equations, and there's a canonical prescription to get the low energy Green's functions. This is due to Kadanoff and Martin. And so I want to emphasize that these are the correct Green's functions at low frequencies and long wavelengths of your fully interacting quantum field theory in terms of a few unknown parameters. So any quantum field theory that you put at finite density and finite temperature, if it has the same symmetries as these, it's going to match. Not just match the coefficients. And what's really interesting is just to study, we don't know a bunch of coefficients, but we can compare Green's functions. So one thing you can do is look at what types of poles you have. Okay, earlier we had a single diffusive pole that was carried by charge density. And so generally, this diffusive pole will still be here. We'll have this type of dispersion relation. But hydrodynamics also has a sound mode. So this pole will have a real part and a small imaginary part. It's carried by energy density and longitudinal momentum. And it will have another diffusive pole. And so what happens when, you might be familiar with what happens if I add a superfluid to this picture. The superfluid couples with charge density and forms what's called second sound. So it basically lifts this diffusive mode into a pair of sound modes. So this pole structure has to be symmetric about the imaginary axis due to time reversal symmetry, and that's why sound modes come in pair, for example. So something similar happens when I add goldstones due to translation symmetry breaking, except instead of coupling with charge density, they couple with momentum, and they lift this diffusive mode to form a sound mode. This is just shear sound. It's basically the same thing that if I hit a solid, act with a shear strain on a solid, the sound wave is going to propagate. This is a sound wave that doesn't propagate in regular fluids, but if you have translation symmetry breaking, you have this shear sound. Okay, good. So now I have this hydrodynamic description. I want to extend its validity by including relaxation. So far I assumed translation symmetry. This is not realistic in basically any condensed matter system. And so I want to include the fact that there might be disorder. Except I'll assume that the effect of disorder is weak, so that translation is still an approximate symmetry. And so if this is true, then I can include it in hydrodynamics in a very simple way, just by looking at my momentum conservation equation and writing down everything I can on the right-hand side, in terms of my hydrodynamic operators, again in a gradient expansion. And so the lowest derivative term I can write down is just this in terms of momentum, which looks like a relaxation term. But in this specific system, there's something else that momentum relaxation does, which is crucial for our result, which is that, remember we have goldstones due to spontaneous breaking of translations. And now I'm saying translations is only an approximate symmetry. So these will actually be pseudo-goldstone bosons, and they'll have a mass. Okay? The usual picture of goldstones in an approximate symmetry, like ions and iron sheets. Okay, good. Now I also want to include phase relaxation. Same way that in a superfluid I wanted the supercurrents to relax. So the reason the supercurrent was conserved is due to the Josephson relation, which says that basically your time derivative of the supercurrent, if I turn off my electric field, will just be 0. But in the presence of, as we know, in the presence of vortices, the supercurrent can be relaxed. And so I'll describe this phenomenologically by adding a relaxation term. So I can do the same thing with my goldstones. There's a little more indices. But if you use isotropy, there's only 2 relaxation terms that you're left with. Okay, this is the Josephson relation for the translation goldstones with relaxation. Okay, so good. So now we have a fully relaxed hydrodynamic description. We can look at what the Green's functions are. And it turns out the conductivity is richer than a usual Drude conductivity. In particular, there's this omega naught, which is the mass of the goldstones that appears in the formula for the connectivity. So this is, again, this formula, the JJ Griggs function. Notice that if I set this to 0, the two factors here cancel, and I'm left again with a Drude connectivity, 1 over gamma minus everything, which would be this red curve. Okay, but in general, with this goldstone mass, what it does is that it shifts the peaks to finite frequencies. So how is this possible? The reason is that there's as many poles as operators that overlap with the current, and usually there's just momentum. But now momentum has a friend. It has the goldstones of translation symmetry breaking are the operators conjugate to momentum. And so the Drude pole that's responsible for this Drude connectivity is actually two poles. It's carried by the momentum operator and the goldstone. And since it's two poles, I can split them without violating time reversal symmetry. I can split them into these two blue poles. And this is a very physical thing. What I'm doing by splitting them is giving the goldstone a mass, which happens if I explicitly break translations. And doing this splitting will lead to this type of shape of the connectivity. So what's nice about this shape is that now the DC connectivity is not large. It doesn't go like 1 over disordered strength. So we have a weakly disordered system, where translations are almost a good symmetry, but the DC connectivity is still not large. So that's the only known way to do that, as far as I know. And another feature of this is that there's these finite frequency peaks. So as I'll argue in a bit, these finite frequency peaks are actually seen in a lot of strange metals. But just before I do that, just 2 more comments. So another hallmark feature of these theories of translation order with relaxation is that there's very large viscosities. For the same reason that a superconductor has a very large connectivity because the charge, the U1 symmetry is spontaneously broken. These systems have a very large viscosity because viscosity basically measures your ability to transport momentum. And because translations are spontaneously broken, so momentum plays the role of charge. So that's why these systems are sometimes called stress superconductors. They're very good at transporting momentum. And finally, you might be a bit dissatisfied with the way I introduced relaxation in these equations. Even though I did it in the most general way possible with symmetries, it kind of seemed like it was coming out of nowhere. So there's a way to formalize all of this using the theory of the memory matrix formalism, which really formalizes this notion of operator overlap and actually gives expressions for relaxation rates if you have a given mechanism in mind that creates this relaxation rate. So for example, if you know what relaxes momentum, then you can give me the Hamiltonian that leads to momentum relaxation. You don't need to give me the full Hamiltonian because that's going to be very complicated, but just determine the Hamiltonian that leads to momentum relaxation, and I can get a formula for gamma perturbatively and how large this perturbation is, and similarly for omega. Okay, so now I'm going to flash some data at you. So we went through a bunch of experimental papers. It was very, very hard. Still traumatized a little bit. And we basically, all these papers look at different materials. They're all high temperature superconductors, except they look at them at temperatures above the critical temperature. So we're in the strange metal phase. And they look at they all plot the AC connectivity. So this is, again, sigma of omega versus the frequency. Okay, and in all these systems, we see that they have these finite frequency bumps in the connectivity. Okay, those are all very different materials, at least looks like different letters to me. And they all have these finite frequency bumps. Okay, here's some more. And I should say, so hydrodynamics is expected to be valid at low frequencies. And so, at some point there's microscopic excitations that will kick in that are non-universal. Here you can see some examples of these that are not captured within hydrodynamics. If I really wanted to capture it, I would have to add some more fast operators in hydrodynamics. And so one thing you can look at, so this is already pretty nice evidence. So we have the fact that DC connectivity is fairly small. We have these finite frequency peaks. We can also look at how the peaks are moving as temperatures increase. So here the temperature is being increased, and you notice that the peak, it shifts the position and the width of the peak increase. And it turns out that for basically all these systems, both the position of the peak and the width of the peak roughly scale with temperature. Okay, so here I spread them using their DC connectivity. This is all these materials. So this is a log scale, so the spread is actually still pretty big, but it's still suggestive that so it's suggested that the temperature is basically the only energy scale in these systems, which brings us back to the fact that they're controlled by some quantum critical point and they're in a quantum critical fan. So one more thing. So if I use the fact that both the position of the peak and the width of the peak scales like temperature, I plug this in my equation here, I'll obtain that the DC conductivity goes like 100 temperature, so that the resistivity goes like temperature. So that's again something you can do with hydrodynamics. You can relate observables. So here we're using AC observables, optic, finite frequency things, to fix the DC conductivity.
Am I supposed to think of the two humps merging into one high temperature?
So they will merge into one if you destroy your translational order. Yeah, I think that would be much higher temperatures.
Well, I mean, all your data looks like
Yeah.
they have peak collapsing onto the red one.
Well, so as the temperature, the position of the peak increases with temperature actually, but everything also gets much wider. Yeah, so the mass of the goldstone doesn't. The goldstones are always there, and the mass grows with temperature. So yeah, if there's a temperature scale at which the symmetry gets restored, it would be above all of this. It would be at very high temperatures.
Sorry, so for example, the second one.
Yeah.
You have the peak. If I go higher up and to the left.
This is lower and lower temperatures.
Lower and lower.
Yeah.
And am I supposed to think of that as going from the blue curve going back to the red one?
Yeah. Yeah. So it can either go smoothly to the red one if the goldstone mass goes to zero fast enough, but it can also go not smoothly. So these relaxation terms go down, this blue curve will approach the red curve, but the DC conductivity will be fixed. It's going to be a pretty singular
Some
limit.
of them looks like.
Yeah, exactly. Yeah. And so these are the ones where the translation order is most rigid, and in others it's restored. So there's one caveat to this whole explanation, which is precisely the fact that everything scales like temperature. And as I told you before, at times of order the temperature, or at frequencies of order the temperature, there's a lot of microscopic stuff that come in. There's a lot, you have non-universal excitations that I should include in my description that should generically appear in these conductivities. So it's, frequencies of order temperature are only marginally within hydrodynamics. Why should you believe me at all? So there's one hand-wavy explanation, which is just to say that this phenomena appears in so many materials in the same way that there should be a simple explanation for it. And hydrodynamics, even though it's not expected to be quantitatively valid, gives a qualitative explanation of where the Judah peak went, okay, and why there's this and a slightly maybe better argument is that even if hydrodynamics is not quite valid at these frequencies, which are ordered at temperature, it's definitely expected to be valid at lower frequencies. And so in particular, it would have to account for the absence of a Judah peak. Okay, so I don't see Judah peaks in the systems. And the contribution of momentum to the Judah peak satisfies the sum rule, so that the integral of the contribution of momentum to the conductivity is some constant. And so it can't hide at very low frequencies. So these are always there can't be a very small Judah peak that I'm not seeing, because it has to satisfy this sum. And so hydrodynamics definitely has to give an explanation for why there's no Judah peak. And this is a pretty generic explanation. It's also nice because with this explanation, this hump isn't coming from extra ingredients, extra particles. It's really still coming from just the Judah peak having been shifted by translational order. Okay. So that being said, it was the fact that everything scales with T suggests that there's some quantum critical dynamics at hand. It would be nice to have an actual quantitative understanding of what's happening using a quantum critical theory. And so similar calculations in the spirit have been done, for example, by Sugir Sachdev, where he does quantum critical calculations for the spin density wave. So the problem with these calculations is that you have a strongly coupled theory at the transition. So you need to find a smart way to resum diagrams. There's a joke. So people say that people in this field always have an expansion that an expansion is a small parameter for choosing the diagrams. That small parameter is 1 over the number of diagrams that you summed. So that all expansions are good. But yeah, basically you need to find a way to resum a lot of diagrams in these theories. And that's typically hard. But there's been recent, very promising advances by some Cyclean collaborators, which basically ignore completely the kinetic term and just look at their tree-level theory just has the interaction term. And so it's possible that these might help perform a quantum critical calculation of these theories. And the goal there would be to get an expression for the connectivity as a function of omega over t and see if it indeed generically has a finite frequency bump when you have a transition between translational order and no translational order.
What's STW?
That's a spin density wave. So it also breaks translation spontaneously, but there's also some kind of rotation, internal rotation that's. But I would have to change the hydrodynamics a little bit to account for the rotations, but I think there would still be this type of finite frequency. Okay, so that's all I wanted to say about high temperature superconductors. In the remaining 10 minutes, I'll talk about another application of these hydrodynamic ideas, which utilizes more the dependence of the geometry, how hydrodynamic correlation functions depend on the geometry of the system you're looking at. So if you remember, our momentum conservation equation in the presence of momentum relaxation had this form. So here I dropped all the high derivative terms, and we just focus on the most relevant terms. So if I plug in the constitutive relation for the stress tensor in terms of the velocity, I'll get what is called the Navier-Stokes equation in hydrodynamics, except here I have momentum relaxation on top of the usual Navier-Stokes equation, which for an incompressible flow has this simple form. So it looks like a Poisson equation with a mass. Okay, there's this intrinsic scale, which basically measures the ratio of the viscosity to the momentum relaxation rate. So viscosity tells you about electron-electron interactions. Okay, the more, if the system becomes more and more strongly interacting, eventually it might saturate the bound of viscosity. And this tells you about electron disorder or electron interactions that don't preserve momentum. And so because of this length scale, the solutions to this equation will depend on the geometry. So the idea is to use that to extract the viscosity of systems. So one of the most simplest geometry you can imagine, a pipe flow. So this is a standard textbook exercise in hydrodynamics. The solution is some parabolic velocity profile. Usually now with this mass, the solution is a bit different, but as expected, the connectivity of this system will be some function of the width of the system, the only length scale here, divided by the intrinsic length scale. And so for very large widths, the velocity will just be constant and will be described by momentum relaxation. But when the width is small, the boundary conditions are more important, and this gradient knows about viscosity. Okay, viscosity basically tells you how fast gradients can go. And so the viscosity will be important for small widths, and momentum dissipation will be important for large widths. So if you can find the width dependence of this connectivity, you can measure the viscosity of your system. And this was used already since the 90s to measure viscosities in, for example, in vortex lattices and superconductors and in other materials. And much more recently, this experimental group used this kind of technique to prove that they observed a hydrodynamic viscous flow of electrons in the system. So this idea was taken to another level by Delacretaz and Falkovich, which also try to utilize geometry, but they want something much more qualitative, an effect of the viscosity, not just a width dependence, but rather something that only a viscosity could do. So what they imagined is they have their sample, and the impose boundary conditions for the current, where you inject the current in a point-like source and drain it in a point-like drain. And so if you have, if your system is not described by hydrodynamics and just by, basically by momentum relaxation, then you'll have a gradient flow of the potential. So this will look like this ohmic flow. But if the system is viscous, there will be backflows or whirlpools of potential gradients. So what this means is that if I measure the potential difference here, if I put my lens here and here, I'll measure the opposite of what you would expect, negative potential, right? So this will lead to negative non-local resistance. And this was actually tested experimentally that same year. So here they had some sample, they injected a current and measured the potential at some points of the system and measured negative resistances for some values of parameters. This was actually the first measurement of the viscosity of graphene. And so the reason this is exciting is that the shear viscosity is a very universal thing that can be defined for basically any quantum field theory. As long as you can couple it to a metric, you can define shear viscosity. And there's a proposed quantum bound that we have from ADS-CFT, the KSS bound on the viscosity to shear ratio. And so now that we have this technology to measure viscosity of electron systems, or many different condensed matter systems, it would be very interesting to see if this bound is typically saturated or violated in these examples of strongly coupled quantum filters.
Is that bound still valid? I thought there were
Yes.
arguments against it.
Yeah, there are examples. Yeah.
You can make large flavor problems for
Yeah.
this bound.
Yeah, there are holographic examples that violate it. So yeah, it's.
Why do we still talk about this bound? Is it something that we don't expect that
Well,
to really
we have-
be a physical thing? Or
So we have no experimental violation of the bound.
isn't there a giant gap between what you can have experimentally and this number?
No, I don't think so. So, right, well, so what is this ratio for the quark gluon plasma?
I
There's
don't know.
one.
203 times the.
Yeah, sure. Not too big.
I see, okay, that's what you mean.
Yeah, yeah.
Okay. Yeah, I was thinking of lists of like liquids and stuff.
Yeah, no, so definitely the regular liquids are not far from this bound, have pretty large viscosities. But these are new strongly coupled systems that may come close to this. So I don't know what the value of this is for graphene. I don't think it's going to come close to this bound for graphene, but maybe ITC superconductors, who knows? It's definitely a special number, because we might not believe it. There might be some O1 factors. There might even be, it could be parametrically violated, but it would be interesting to know what nature tells us about whether this bound is satisfied. Okay, so here I define the shear viscosity as a two-point function of the stress tensor. Within hydrodynamics, you can also view it as a term in the constitutive relation for the stress tensor. Okay, so here the zero derivative term is just the pressure. This is the perfect fluid approximation. And then you can generally write down higher gradient terms. I can always write down a shear viscosity as well as a bulk viscosity. So the bulk viscosity doesn't have a bound as far as I know. I think the main reason for that is that it vanishes in CFTs. So we don't have the same tools to study it. It vanishes because the stress tensor has to trace this. But in 3 dimensions, in 2 + 1 dimensions, if I don't have parity, there's one extra term I can write down, which is called the Hall viscosity. Okay, so it comes at the same order in derivatives, except it's a bit different because it's parity in time reversal odd, and it's non-dissipative, so it doesn't contribute to entropy production. So for that reason, there probably won't be a similar type of bound on this quantity. However, it's still very interesting mathematically because it's quantized and known in certain contexts. For example, in fractional quantum Hall systems. And so I think this was first derived by these people for quantum Hall states. So you can use the adiabatic theorem to compute the Hall viscosity in a quantum Hall state. And that the basic idea is that let's imagine we're in the ground state of the system, and that my Hamiltonian depends on some external parameters. So this is what the adiabatic theorem tells me, that this object here is equal to how the energy varies in terms of the parameters plus this very phase term. And so if I imagine that these external parameters are deformations of my system, the response of the Hamiltonian to deformation is kind of like a stress tensor, expectation value of a stress tensor. And deformation dot is like a velocity. And so you can kind of convince yourself that this kind of looks like a viscosity. Also, this happens to be odd under time reversal symmetry. So it really is the Hall viscosity. And so for some smart choice of these external parameters, you can exactly compute what the Hall viscosity is. So for example, for the integer quantum Hall state, it's given in terms of the filling fraction mu by this expression. And for the Lofton state, the expression is slightly different, but it's always quantized. So nu is basically the quantized Hall connectivity. And the Hall viscosity is related to the same quantization. And so what's and it also has a geometric interpretation. If I write down the effective action for these systems in terms of background fields, it will be the coefficient of the Wendt term. So a term that couples your U1 source to the gravitational source. It's roughly integral. Something like this. And also what's exciting about it is that it has never been measured. So these ideas, this has never been tested. Even though the Hall connectivity has been tested and is one of the most precise things we can measure, this has never been measured. So the idea is to use a similar method as what has been used with Hall viscosities, to extract Hall viscosity, what has been done with shear viscosities, now with Hall viscosities. So measuring the actual profile of the velocity is very hard. So instead we're going to take inspiration from what has been done with Hall, with shear viscosities by doing non-local connectivity measurements. And the reason this is possible is that the Hall viscosity appears as a k-squared correction to the k-dependent Hall connectivity. So here if I write the connectivity as a function of k, the leading term is just the quantized Hall connectivity. And there's this k-squared correction which is proportional to the Hall viscosity, plus higher order terms in k. And so generically, this will depend on the geometry. So it's still a bit challenging because this coefficient here, this length scale, is the magnetic length, which is extremely small in these systems. But there's still some hope that this might work because it's an area where the experiments are extremely well controlled. In fact, it's even how the quantum of conductance is defined with these experiments. So the idea is to try to find some corrections due to either inhomogeneous magnetic fields or different geometries to measure this Hall connectivity, Hall viscosities. Okay, so to summarize what I've been telling you, connectivities have a lot of information on your interacting quantum field theory, especially if you can probe the whole function as a function of frequency, K, geometry, temperature, and external fields. It'll help you distinguish between different hydrodynamic descriptions, different assumptions about symmetries. So I didn't mention what types of flow a fluctuating superconductor could have, but that would also be a way to distinguish, because as we saw, a superconductor can have a Juda connectivity like a regular Juda conductor. So you could use flows to distinguish these two systems. There's some other related ideas in this direction. One of them is to explore the Stokes Paradox, which is a statement in hydrodynamics that if I have a flow through a channel and I put an obstacle, the linear response basically breaks down, meaning that the velocity, the electric field I need to use to drive this flow is not proportional to the velocity. And so you can kind of play around with this in these systems to see typical hydrodynamic signatures. Also, we've been working with an experimental group on trying to work with different Green's functions. So once you're tired with this one, you can look at Green's functions of the thermal currents. So this can be defined even if I don't have a conserved U1 charge, so it's an even more general observable, but it's a little harder to measure. And so that's something else that can help constrain your hydrodynamics.
What's conserved in that case?
So this, you can build it from the energy current. So as long as you have energy conservation, you can build such. Typically, it's a combination of the energy current and the charge current, even if you don't have charge. So time transitions, so which is hopefully satisfying. Okay, so that's all I wanted to